So the task that I'm going to be looking at today as a concrete task is this CLEVR data set. So it's an artificial visual question answering data set that was made by Justin Johnson while he was interning at Facebook AI Research. So here's an example of an image and a question. There is a purple cube that's behind a metal object left to a large ball. What material is the cube? So these questions have the kind of complex compositional questions which are custom designed to be good places to see whether you can understand and reason. So if we just walk through for a moment what you have to do, you start with there being a purple cube, so there are a couple of purple cubes, then it says it's behind a metal object, so there's a metal object and the things behind it, then left to a large ball, so there's a large ball and the things left to it, so that pretty much narrows it down to a certain purple cube, and then it asks what material is the cube. And you probably think, gosh, I don't know, what material is that? But it turns out in the CLEVR data set, there are only two materials. Things are either metal or rubber. So if they're not shiny, they're rubber. And so the answer is that this is rubber. So that's the main setup of the problem, but something that's important to note that's down the right-hand column is each instance in CLEVR is accompanied by a functional program, which is sort of, you can think of it kind of like a database query that specifies various filter and select and relation operations, which will compute the answer to the question. And that's important because some of the other models that we'll look at make use of that data. Okay, so the CLEVR data set, it's another of these sort of artificial generated data sets. It's not a real problem in the world. So starting off on the visual side, these are photorealistic images of 3D objects in a few shapes, colors, materials, and sizes. They're actually all made in Blender, if you have kids that use Blender. It's accompanied by these highly compositional multi-step questions which seem good for assessing reasoning. And then as I mentioned, there are these tree-structured functional program representations. So it's actually the case that the language of the questions also isn't really natural language. The language of the questions is actually generated from these functional program representations by rule. So actually in the basic version of CLEVR, we don't actually have a natural language understanding task. We have artificial controlled language understanding task. Nevertheless, it requires a variety of reasoning skills such as transitive inference, counting, and comparison between attributes and amounts. And to make my natural language processing self a bit happier, alongside the CLEVR data set, there is then the CLEVR humans data set, which then does have genuine human-asked questions collected from Mechanical Turkers. But the strengths of CLEVR are, well, by the construction of the data set, it allows thorough analysis of performance based on the question's structure and type. But more particularly, part of why it was originally designed was there was this first generation of visual question answering work, and it looked impressive initially, and then people started to discover that there were a lot of question conditional biases and opportunities to do spurious and superficial reasoning. So it seemed that most of the initial VQA systems didn't actually understand much about either language or the images. So you got things like if the question was asking what covered the ground, you didn't have to look at the image, the answer was always snow. And so CLEVR was put together precisely so that would not be the case, and that you actually had to understand the language and the picture in order to be able to answer them correctly. There's been a number of previous pieces of work that have already looked at the CLEVR data set. They basically fall into two groups. So the first group is the neural module network approaches. So these were pioneered by Jacob Andreas and colleagues, and there's also been an approach pursued by Justin Johnson and colleagues. And essentially, these models treat it like a semantic parsing problem in NLP terms. So all of these models make use of the strong supervision that comes from the functional program. And so what you're doing is a two-stage operation. The first stage is that you use a sequence-to-sequence model to translate the English form text back into the functional program using the strong supervision. And then the second phase is actually the neural module network, where you use the functional program to piece together custom neural network pieces. So there's a discrete collection of specialized neural modules for doing things like selecting, filtering, counting, comparing, and they're stitched together based on the functional program, and then they run. More recently, there have then been a new class of models which don't use the strong supervision, and essentially they are large ConvNet stacks interleaved with some kind of specialized layer. So the first such system was the relation nets done at DeepMind, and the relation net layer that's stuck in between the convolutional layers takes every pair of pixels in the image and considers a relation between them and makes predictions based on those binary relations. And then more recently again from the University of Montreal is the film system. And it also sticks layers inside the convolutional network stack. But this time they're kind of like a controllable normalization layer where the processing of the question tilts the normalization that happens between the layers. It's a little bit harder to get an intuitive sense as to why that's a useful thing to do, but it is. Okay, but now what I want to do is move on and tell you about the memory attention composition networks that we've designed. So the idea of this network is how could we custom design from the ground up a neural model which has a better structural prior for problem solving and reasoning tasks. And building on the success of sequential models, that this model is explicitly a sequence model, but it's designed to be more constrained in such a way as it encourages it to do a sequence of explicit reasoning steps, each of which is performed by a MAC cell, a memory attention composition cell. So in particular, as a recurrent network, there's one universal MAC cell that is used throughout all the steps. But its parameterized design is such that it's versatile and it can adapt its behavior and context to perform different operations. So we don't need kind of custom networks for every different kind of reasoning operation that we want to do. This network will then make use of self-attention, so it can actually simulate arbitrarily complex reasoning graphs using self-attention while maintaining end-to-end differentiability. Okay, so we'll then, for the next few slides, gradually work down into the details. So for a single MAC cell, it's meant to do one reasoning step. And to do that, it makes use of having two recurrent states. So we have a control state, and so this represents the step's reasoning operation. And the reasoning operation is going to be represented as an attention-based average of a given query, where the query for CLEVR is going to be the question that we're asked. And then we also have a memory state. So the memory is going to store retrieved information that's relevant to a query and can be accumulated over steps. And so it's actually also going to be represented as an attention-based average, but it's going to be an attention-based average over what in general I'd like to suggest is the knowledge base. But for the work I'm presenting here on CLEVR, our knowledge base for answering questions is simply looking at an image. Before we get into the details of the MAC cell, we need to have a knowledge base and a query to feed into the MAC sequence. And there is a pre-processing layer that uses pretty standard methods of neural network pre-processing. So for the query, it's processed by BioSTM, and that yields a sequence of contextual words, the hidden layer of the BioSTM, and an overall query representation that's formed in the standard way by concatenating the final forward and backward hidden states. For our so-called knowledge base, that is the image, we're using a completely standard ResNet stack. Indeed, we're using the one that Justin Johnson made, and then using the output of that as our knowledge base representation. So in slightly more detail, here's the picture for the MACnet. And so the first thing to notice is that it has two recurrent states. It has a control state and a memory state. And so there is a fundamental idea here, which is to think maybe there's actually something good in the kind of architecture that's been used throughout the history of computing, where control and memory are separated from each other. At any rate, that's a hypothesis that's being developed in this work. So the control unit computes a next control state, extracting an instruction from the query. Then the read unit retrieves information from the knowledge base, given both the previous memory, it's again working recurrently, and the current control. And then finally, the write unit is going to update and write the next memory, merging the newly found information with the previous memory to then write the next memory. So quickly, in one more level of detail, though this is probably getting to be slightly more detail than you could absorb off PowerPoint slides, but I'll just sort of say a minute or two about how we get down into the details of what things do. Okay, so this is the control unit. So the control unit has as its inputs the previous control state, the query that's the summary of the query to perform, and the contextual words. And so first of all, it calculates a time-specific query representation through a linear layer. Then it combines that with the preceding control instruction. And then at that point, it uses a particular architecture which we both thought would be very useful for interpretability and proved to be very successful performance-wise, which is our calculated representation, CQI here, is projected down onto the actual words of the query. And the way that that's done is in the standard kind of attention way. So we put an attention distribution over the words of the query, and then we calculate a weighted average of those words. The read unit is the most complex part of the system. So it takes the previous memory and the knowledge base. So first of all, it's going to be considering each item in the knowledge base, which is sort of the outputs of the conv filters. And first of all, it considers relating them together with the previous memory. So this is a facility that makes it easy to do transitive reasoning, because the preceding memory can guide you to what to get next from the knowledge base to reason transitively. But we don't only want to do transitive reasoning. Sometimes we'd like to be able to combine multiple memories together, such as when we do logical operations like or and or counting. So we again combine the output of that with accessing over the memory. Then we also want to consider what to do based on the control that we've calculated. So the control feeds in, again, doing a Hadamard product, and then at the end of that, we're again doing a projection via attention back onto the knowledge base items, and this attention weighted average then becomes our candidate new memory that we pass forward. And then there's the write unit. We actually explored a couple of write units of more or less complexity. The simplest write unit is you take your newly calculated memory and your previous memory, and you put it through a linear layer, and you write it as your new memory. And it turns out that actually works pretty well. But you might think that sometimes you've got to do a hard amount of thinking and sometimes only a little bit of thinking. So it might be useful to have a highway gate so that once you've finished your reasoning, you can just easily pass through your preceding memory. Or we had this idea of using self-attention, where you could use all of your memories to help guide the next memory. And so we could put in a self-attention layer so we can make an explicit DAG of inference steps. So concretely, the way we do this is we then use a kind of a key value memory network idea, so that we're taking the attention distribution between preceding control states and using that to access preceding memories. Okay, so that's our MAC network, our MAC cell, and the way we make our whole MAC network is then just using these recurrently, and in particular allowing it to be directed acyclic graph using attention. So this gives us a fully differentiable end-to-end model for reasoning. The final bit we have to have is network outputs. This is actually very easy for CLEVR. There are actually only 28 possible answers. There's yes, no, there's colors, materials, comparisons. There are numbers, but all of the numbers are single digits. So there are only actually 28 answers, and so we simply use a 28-way softmax. And so this takes in both the memory and the final form of the query. Using the query at this point is vital because of the way that the MACnet segregates the query from the memory, that the memory does not really represent the query and it has to be combined in again. Okay, so here are some of the experimental results and a bit of discussion. So in the CLEVR data set, overall there are 700,000 training examples, 150,000 test examples, the 28 answers. Because there are a limited space of answers, the baseline is very small. There are lots of yes-no questions or metal versus rubber questions. And so if you guess the most frequent answer for each question type, that gets you to 41%. Using ConvNets and LSTMs is sort of the standard baseline VQA architecture. That does a bit better, but not a lot better. That gets you 52%. Jacob Andreas's initial neural module network work did a lot better than that. That got you to 83.7%, which seemed to be heading in the same direction of some of these tasks where you were kind of closing in on what was measured in the original paper as the performance of humans, which was 92.6%. But remember that this is a completely artificial and task with artificially constructed language and deterministic answers. So there's actually no reason for this task why you shouldn't be able to get 100% right. And actually there's a bogus reason why the humans tend to perform a bit imperfectly, which if someone wants to ask, I can explain later. So because of that, actually in recent work, all of the action has moved to the 95 to 100% level. And so that started with DeepMind's relation networks, which got just over 95%. Justin Johnson's second generation neural module networks get 96.9%. Film got 97.7%. And you're probably expecting that it turns out the MACnet does better again, getting 98.9%, more than halving the previous error rate. But nevertheless, these numbers are getting so high, you might be sort of suspicious as to how much signal there is there. I think there is signal, but maybe it's more interesting to look at some of the details. So in basic CLEVR, there are 5 kinds of questions. There are existence questions, does something exist? There's querying an attribute and comparing attributes between 2 things. And all of these 4 systems get over 97% on all of those. The harder kinds of questions are the ones that involve numbers, comparing numbers and counting. And so in particular, previous systems had the most difficulties with counting questions. So both the relation networks and the second generation neural module networks got about 90% on the counting questions. Film did rather better, and then MACnet is doing a lot better again on counting questions. But even for MACnet, the class of examples it does least well in is counting questions. And this might make you wonder whether having more of a counting primitive would actually be also a useful kind of structural prior to consider putting into a reasoning system. Here are a couple of more interesting results. So how fast do these models train? That's a good reflection of whether they have good inductive biases. Trying to use LSTM plus CNN plus spatial attention model, it learns very slowly, that's the bottom line. Film and the second generation neural module networks are better again, but MACnet trains much faster again. So in 2 epochs through the data, it's performing as well as the neural module networks are performing after 10 epochs through the data. And I think you can take that as stronger evidence that this model does just have good inductive biases that help it to learn. Here's another demonstration of this looking at a learning curve by restricting the amount of data that you train on. So if you train on 700,000 examples, several of the models do very well indeed. But if instead you say, let's just train on 70,000 examples, 1/10 of the data set, what you then find is all of the other good approaches like Film and Justin Johnson's neural module networks are getting at most 51.6%. Again, not really that much more than the 42% baseline. Whereas MAC is still doing really well. Even 70K examples is enough for it to get 86% correct. Then here's our real human language, the CLEVR humans data set. So it consists of 18,000, a small number of real human language examples coming from crowdsourcing. So the humans were instructed to write questions that would be hard for a smart robot to answer. In particular, they were able to ask any kind of question which could be semantically quite different to the only 5 types that the systems were trained on. That data set was regarded as too small to actually train on. So the first thing people have done is just a blind transfer task, and here are the results from that. And then the second thing is that there is a corresponding dev set or adaptation data set for clever humans. So people will then adapt on that data set and then see how well you do. And so if you do that, what you notice is, well, not only does MACnet win again, but MACnet is actually gaining differentially more in doing the adaptation, which again I think reflects the fact that it has good inductive biases, so it can generalize much more quickly on that data. Okay, here are a couple of pictures. Because of the fact that the model uses attention both to the query and the knowledge base, you can have a fairly concrete idea of what the model is doing. So this question is, what color is the matte thing to the right of the sphere in front of the teeny blue block? Now, for the length of the sequence model, you get the best results by running it with a reasonable length sequence model of running it with a length of somewhere between 8 and 16. But for showing pictures, it's better to have a shorter sequence model, and it still performs fairly well with the short sequence model. So what we find is for the first time period, it focuses in the language on teeny blue block, and it finds the teeny blue block in the picture. Then it focuses on the sphere in front of, and it finds the sphere in front of, and then it says what color is the matte, and it focuses on the what color is the matte, and it answers it correctly and gives the answer purple. Here's a more complex and harder to see example. How many objects are either small objects behind the teeny metal cylinder or metallic cubes in front of the large green metal object? I can barely read this myself. Interestingly, what you notice here, and this is quite common in the way it behaves, is it'll then, with a longer sequence model, it'll use the first couple of steps to absorb semantics. So at first it's focusing on how many and small, then it's focusing on the fact that this has a disjunction in the condition, and then it starts looking at large green metal object, and looking for metal cubes in front of that. And you can see there it's found the large green metal object, and it's then looking for the metallic cube in front of that. And then it moves back to the first half, the teeny metal cylinder, and then looking for small objects behind that. And at time step 5, it's finding the teeny metal cylinder and then the small objects behind that. And so this is actually enough information that it can successfully count, and it gives the right answer of 4. Here are a couple of clever human examples, just one off, which sort of show the different kind of semantics of questions that's being asked in clever humans. So what is the shape of the large item mostly occluded by the metallic cube? What color is the object that's a different size? What color ball is close to the small purple cylinder? So we've got notions like occlusion and close to that were nowhere in the original semantics. Okay, so I hope to have shown to you that this works pretty well. Let me just quickly emphasize, how does this differ between MACnets versus module networks? So neural module networks are also an architecture that speaks to Leon Batu's vision, that they're also composing together pieces to do more complex inferences. But I think this model is advantageous because we're making use of one universal and versatile cell that's used across all states, sharing architecture and parameters. And indeed, we did some ablation studies. You actually get worse performance if you don't share the parameters in a sequence model manner. But this cell can adapt its behavior based on the context in which it's applied. In contrast, the neural module networks have a discrete fixed inventory of really rather task-specifically designed specialized modules with distinct parameters and even architectures. So they lack the generality, and they lack any of this concept of sharing and universality. Against the Phil model from Montreal, we actually did take a key insight from the Phil model. So the Phil model proposed a model in which, rather than transforming both the query and the knowledge base into the same representation, it proposed an indirect modulation. And we've sort of borrowed that kind of indirect modulation. But I think we really benefit from having our close attention to the query and the knowledge base, where Phil's conditional normalization layer is kind of a global tilt which is applied identically across all image reasons and doesn't allow the kind of selective behavior based on features or positions. Okay, so I hope that I've shown you this idea that maybe there are interesting things we could do to push neural networks to do higher level inference and reasoning, to get back to what artificial intelligence was meant to be about, where we would have thinking going on in our neural network architectures. I've proposed a particular design for doing that, which is a form of constrained sequence model separating control and memory, and particularly exploiting attention as a good model for reasoning. And I've argued that it has strong compositional reasoning skills and the right kind of inductive bias to be able to do well in these kind of tasks. And it's practical as a generic, fully differentiable end-to-end model. Now, is this the one and only true answer as to how you could design a neural network more for reasoning? I'm sure it is not. I'm sure there are lots of other ways and variants that people could think of exploring. But I think it is an interesting challenge for the community to actually be putting more effort to be thinking about what are a few more different and good building blocks that we could be using in neural net architectures rather than being so dependent on such a very small vocabulary of ideas as so much of the work in the field has been in recent years. Thank you.
Okay, we have time for some questions. Dimitri?
Thank you. Great work. It's an interesting idea to separate control and memory, but then what happens is that you decide which steps of reasoning will be performed regardless of what result from the knowledge base the previous steps of reasoning fetched. So you decide in advance what reasoning you'll do, and you don't look at what you retrieve. Do you think this has some limitations?
So that's a great question. So I actually think that you're pinpointing one of the deficiencies of this current architecture. So it seems like a key thing that you'd like to be able to do for reasoning in general is you're searching your knowledge base. You've discovered that a person was born in Poland, and therefore you say, okay, well, I'm going to take that fact and incorporate that and start looking for other people in Poland that they might know or whatever it is. So you want to have the memory feeding back into the control to determine future actions. And I think absolutely that's true, and that's something that should be incorporated into a MACnet version 2. It sort of happens that for the particular design of CLEVR, you don't have to do that because you are really sort of following the instructions that's in the question. But I think that's a key avenue that's a deficiency that should be addressed in the future.
Thank you.
I think we have time for at least another question.
There's a lot of work on making neural networks explainable or interpretable, and it seems like in reasoning, it's important not to just get an answer, but also why did it give that answer? Do you have any thoughts on making it more interpretable or explainable?
Okay, partly not. So it was actually one of the hopes in the design of this architecture that it would be a model that was transparent, interpretable, and explainable. And that was initially a motivation for grounding both halves of the model as doing attention distributions over the query and the knowledge base. And I mean, it was really kind of then a lucky side effect that we found that actually improved the speed of learning and improved performance as well. So in one sense, there are these lovely attention pictures that I can show you, which makes things kind of interpretable. But on the other hand, I mean, as a lot of us know who've looked at attention pictures, it's kind of easy to tell just so stories about them, and you can never be quite so confident as exactly what it means as to what the thing is doing. You can show that there's good localization over time, but it's hard to tell whether it's really computing in back of or doing greater than. And so I think there's sort of more work to be done for that. I'm not sure I have a specific answer to that, but clearly various ideas people are starting to explore, such as generating text alongside the models to have them explain what they're doing.